making a video for you with notes about the Chapter 6 test to help you study for it and understand the concepts that are going to be covered in this unit about the normal distribution. So the normal distribution is a distribution that has a mean of 0 and a standard deviation of 1. So the first question on your test is an example of that. And now we need to find the probability. Okay, now the mean is 0, so 0 is represented by the very middle of the graph. And so 1.5 and 2.25 would both be towards the right. So I picked the answer that had 1.5 and 2.25 towards the right side of the graph. And then I want to indicate the probability of a temperature between those two values, which would be that blue area. Now I want to find out how big that probability is of getting a temperature that's between 1.5 and 2.25. So I can use page 2 of this table. Positive z-values are on page 2, negative z-values are on page 1. So look at that number 1.5 and let's find that on this table. So 1.50 is right here, 0.9332. So 0.9332. Now that's not the final answer. I'm just typing that in so I can remember what it is. That's not the final answer though. Now I need to look up the value for the z-value of 2.25. So I click on page 2 again, and z-value of 2.2 is right there. This first number is 2.20. This is 2.21, 2.22, 2.23, 2.24, and 2.25. So 0.9878. Now the probability of getting a reading between those values is equal to the difference between those numbers. So I need to subtract them from each other. So I'm going to take this bigger number minus the smaller number and subtract those like that in order to get the answer. So I'm just going to do that on my phone real quick. 0.9878 minus 0.9332. And what I get is 0.0546. So run it off to 4 decimal places, it's 0.0546. Now I'm also going to show you how you can find this answer using the StatCrunch program. So these tables that they have, this is the way that they've done it for many years. Mathematicians use calculus to calculate the integration of the normal distribution, and then they print out the results on a big table so that other people can find the answers out to calculus problems without ever needing to use a computer at all. So those z-tables are very important. Those z-tables are the only way you can do statistics without having a computer. Except we have computers now, so we don't actually need to look at an old-fashioned piece of paper and find the results to statistics problems. Instead of that, we can click on programs like StatCrunch, and then we can click on Stats, Calculators, Normal. Click on that, and then what we're going to do is we're going to click on the word between, and then we're just going to look at the original numbers. It says a mean of 0, standard deviation of 1. So make sure it already says that. It says that. Mean 0, standard deviation 1. Then find the value between 1.5 and 2.25. So 1.5 and 2.25. Then you click compute, and there we go. We get an answer of 0.0545, but notice that 8, because of that 8 I need to round this 5 up to a 6. So 0.0546, and that's exactly the same as what I got from the table. So for the rest of the problems on this, on these notes, I'm just going to use the table or the calculator that's provided from StatCrunch, although you could look them up in the tables on paper as well. Okay, so now this one says the mean is 0 and the standard deviation is 1. So I'm going to go ahead and open up that StatCrunch window again. and then click Stat Calculators Normal. And then I'm going to it says draw a graph that represents the 20th percentile. And it even helps you out. It says this is representing the separation between the bottom 20% and the top 80%. So if you're at the 20th percentile, that means you're better or higher than 20% of the data. So P of 20 would be over to be on the left side, and so it should look like this. Now this is representing the right side. This is also representing the right side. This is representing the left side, but that's more than half of the graph. P20 is only 20% of the graph, so that C is the only option. Okay, now let's find the bone density score. Okay, so by bone density score, it means find the normal distribution value. So we're going to use StatCrunch to find the 20th percentile. So we want the red area, instead of the red area right there represents 50%, let's change that to be 0.20, 20%. Ready? Okay, so the Z value that represents 20% of the area is, now this means below, so 20% of the area is below. It's that number right there. Now round it off to 2 decimal places and I'll get negative 0.84. Perfect. Now, that's it on that problem. So on this one it says, draw a graph and find the bone densities that's separating the lowest 17% and the highest 17%. So it's going to have a little bit on the bottom side, the lowest 17%, and a little bit on the right side, the highest 17%. So it's going to look like that. Now I'm going to find the normal distribution z-scores that can be representing those two values. So I'm going to click on between. Okay, so now here's a critical thinking problem for you. If you want to know what value cuts off the lowest 17%, click on standard. Now click on this to be less than, that means the lowest, and then type 0.17. So click compute. So the value that separates the lowest 17% is equal to negative 0.954, etc. So that's going to be the first answer. Rounded off to 2 decimal places, it's going to be negative 0.95. So then put a comma. Now, let's try to find the other side, the other side it says the highest 17%. So what would that be? So that would be, now wait, this is the lowest 17%, so I need to change this to be greater than. So this is going to, but see how that changed? I need to change that back to be 17% again. So now click compute. See that red area, always make sure it represents what you're trying to find. So that now represents the highest 17%. And the z-value of that is equal to that. Positive 0.954. Now notice the z-value of the cutoff of the highest 17% is actually the same number except positive as the value that separates the lowest 17%. And you can see that that this graph is symmetric. So if you're doing the lowest percent and the highest percent and they're the same percents, then you'll always have normal distribution cutoff scores that are just the same value but negatives and positives. All right. Then problem 4. Find the indicated area under the curve of the normal distribution. So between the score of z equals -1 and the score of z equals 1. So ready? Click on between. So leave that the same. Now click -1 and +1, then click compute. So I found out that number. So I enter that in. Now I round that out. First I convert it to a percentage. So that's a decimal. I need to move this decimal point over by 2 places. So move it from, hold on, let me zoom in a little bit. It's kind of hard for you to see that decimal point. So I'm going to move that decimal point over to there. And then I'm going to round it off to 2 decimal places. So I'm going to round it off right there, but notice that's an 8. So anything 5 or bigger you round up. So that 6 becomes a 7. So 68.27%. Okay, now this problem says assume that adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 15. Find the probability that a randomly selected adult has an IQ less than 124. So this works the same way, except in order to find the z-value of 124, we need to do a formula. So the z-value equals the actual number, which is called x, minus the mean, divided by the standard deviation. So we'll get a z-value that is equal to, the value of the adult is 124, and the mean is 100, and the standard deviation is 15. So I'm going to calculate this. It's equal to 24 on top, 15 in the bottom, and 24 divided by 15 equals 1.6. So the z-value is 1.6. Now, I really just need to think about that 1.6. But that's not the answer, though. That's just the z-value. So I need to find the probability a randomly selected adult is below, so ignore the 124. I need to find the probability that there will be below 1.6. So ready? Click on standard, and then right here, click below, less than, and then enter 1.6, and click compute. So the probability is 0.94. And then you round that off to 4 decimal places, which is like that. Now, there is actually a better and easier way of doing it for you. With this software, you don't have to actually find the z-score directly. I'm going to show you this. Ready? So instead of doing all that work, which wasn't very hard, but you do need to remember that formula for how to find a z-score, though. The z-score formula is the number minus the mean all over the standard deviation. That's the formula that I showed you. However, though, you can still use this software to find the probability that something is less than 124 by doing this. See this number 100? The mean is 100 and the standard deviation is 15. So do mean of 100, standard deviation of 15. Now this is not the standard normal distribution, but this is still another normal distribution. So if you change the mean and the standard deviation, then you can also change the value to be 124. So now we're going to find the probability that it's, we're going to find the probability that an IQ is less than 124. So we'll type in mean of 100, standard deviation 15, then find the probability it's less than or equal to 124, and then click compute, and you'll get the same exact number, 0.9452, like that, 0.9452. Okay, now we're done with that one. So then we're going to use that same technique for more problems as well. So this one says, what's the minimum table occurrence required to satisfy the requirement for the min? So let's type in the values for the min. The values for the min are 21.4 is the mean. So 21.4, hold on just a second. So the mean for males is 21.4, and the standard deviation for males is 1.3. And they want us to find what's the minimum table clearance so that 95% of men can fit their knees underneath the table. Okay, so that means that you want the probability that their knees will be under the table to equal 0.95. So click compute. Okay, so if the average male has a knee height of 21.4 and a standard deviation of 1.3, then that means that if you want to have 95% of males be able to fit their knees underneath the desk, then you need to have the desk be at least 23.53831 inches tall. So there we go. Round it off to 1 decimal place, so that rounds off to 0.5. Now, determine if the following statement is true or false. If there is clearance for 95% of males, there will certainly be clearance for all women in the bottom 5%. Well, the bottom 5% of women means the 5% of women who have the shortest knees. The very shortest 5% of the knees of women. Well, if the table is tall enough so that 95% of men can fit their knees under it, then that includes even some of the taller men. Not the very tallest, but even a lot of the taller men will be able to fit their knees under it. So that would include the women in the bottom 5%. So that statement would be true because the 95th percentile for men has longer knees or is greater than the 5th percentile of women who would have shorter lengths of knees. Okay. So the author is writing this exercise as a table with a clearance of 23.9 feet above the floor. What percent of men fit this table? So let's go back to this calculator again. 23.9. So what percent of men will have knees that can fit under that table? So we're going to change this to be 23.9, and then this box will show the probability of how many men can fit under that table. So if the table is 23.9 inches above the floor, then this is the amount of people who can fit their knees under it of the men. So put that in. That rounds off. Change that to a percentage, so move the decimal point over to be right here. And then round this up to 28. And then what percent of women fit this table? So this is still talking about the table with the clearance of 23.9. So the clearance is still 23.9, but women have a different standard deviation. So it says females have knee heights that have a mean of 19.3 and a standard deviation of 1.2. So now what's the probability for the women that their knees will be able to fit under a desk or a table that has a height of 23.9? So that's equal to 0.99993679. And if I move the decimal point over twice to convert it to a percentage, it'd be 99.99, rounded off to 2 decimal places, so that it'd be 99.99%. Does the table appear to fit almost everyone? Well, no, because this table only fits some of the men. See, for the men, it only includes about 97% of the men. So there's actually 3% of the very tallest men who will not be able to fit at this table. So the answer would be that this table will fit almost everyone except for about 3% of the men with the largest sitting knee heights. Okay, now assume the military use ejection seats for men between 142 pounds and 215 pounds. So let's just see. If women's weights are normally distributed between, so the mean of women is 163.3, and a standard deviation of 49.7. 163.3, 49.7. Those are the women's weights distribution. And now let's click between. So mean is 163, standard deviation is 49.7. And now we want to find out the probability that the women, which have those that distribution of their weights, can fit into an ejection seat that is between 142.8 and 215. So this is the probability that someone can fit between those two numbers. And so that's equal to that. So that equals, so move the decimal point over, then round it off to 2 decimal places. So the 51.08 becomes 51.09. So about 51% of women have weights between those limits of the ejection seats. Are many women excluded in these specifications? Yes, a lot of them are, because only 51% of them can fit. So that means that about half of the women cannot fit. So yes, the percentage of women who are excluded, which is the remainder or the complement of the probability found previously, shows that about half of the women are excluded. So I would choose that one. All right. Okay, assume the human body temperature is normally distributed with a mean of 98.23, mean of 98.23, and a standard deviation of 0.61. Okay, now a hospital uses, so let me click on this button, standard. A hospital uses 100.6 as the lowest temperature to be considered a fever. So we want to find out what percent of normal and healthy persons would be considered to have a fever. So the mean is 98.23, the standard deviation is 0.61. They are considered to have a fever if their temperature is greater than or equal to 100.6. Now I'm going to click compute to find that probability. The probability is that, so that many people would be considered to have a fever who are actually healthy people. So there's not very many healthy people who would have a fever. Now, before I forget, let me move the decimal point over to there, and then round it off to 2 decimal places. So since there's a 5 after that, this rounds up to 1. So there's 0.0, oh, oops, I'm sorry, I don't need that. I don't need 2 zeros there. So there's 0.01. The percentage of normal and healthy persons considered to have a fever is 0.01%. Does this percentage suggest that a cutoff of 100.6 is appropriate? Well, I would say yes, because there's not very many healthy people who actually have fevers of 100.6. So now there is a small probability that it could happen. So I would say yes, that's a good cutoff, because there's only a small probability that a normal and healthy person would be considered to have a fever. Okay, the minimum temperature for requiring further medical tests should be what? So now it's asking us, well, what if we wanted to choose a temperature for somebody so that only 5% of healthy people would be higher than that temperature? Well, remember, the mean and standard deviation of healthy people is that. So we want to get the probability of something to equal 5%. So if 5% is 0.05. So the result would be 99.23336. Okay, so the minimum temperature for requiring further medical tests, rounded off to 2 decimal places, should be 99.23 degrees if we want only 5% of healthy people to exceed it. Now this is what the problem on your homework wants you to do, but this is probably not actually a good temperature, because if they use this temperature to require you to have further medical attention, then this means that 5% of all the healthy people in the whole United States would immediately have to go to the hospital. And that would be more than 10 million people who are actually healthy would immediately have to go to the hospital. So the hospital probably should not actually have a temperature at which 5% of healthy people would exceed it. So a cutoff of something like 100.6 is probably a better value to decide whether somebody might be sick or not than 99.23. That's just a comment though. The answer to this problem is still 99.23. Okay, which of the following statistics are unbiased estimators of population parameters? So sample variance can be used to estimate a population variance. Sample mean can be used to estimate a population mean. And sample proportion can be used to estimate a population proportion. So those are the three: sample variance, sample mean, and sample proportion. Okay, when two births are randomly selected, the sample space, meaning what could happen is you could have a boy and a boy, boy and a girl, girl and a boy, or a girl and a girl. And assume those four outcomes are equally likely. So construct a table that describes the sampling distribution. So you could have, if you had two births, you might have a proportion that was 0 girls, or you might have a proportion that was half girls, or you might even have a proportion that was all girls, right? Because if you had one boy and one girl, it'd be half girls and half boys. If you had 0 girls, it'd be 0% girls, and if it was 2 girls, you'd have 100% girls, which would be a ratio of 1. Okay, so the probability, now there's 4 outcomes, right? The probability of having 0 girls is 1 chance out of 4 chances, right? So 1 out of 4 is the probability of that. Now, how many times could you have 1 girl and 1 boy? That could happen 2 times, right? There's 2 chances out of 4, but 2 out of 4 reduces to 1/2. And then you also could have a proportion of 100% girls. That could only happen if you had both girls, which happens 1 time out of 4 possible chances. So the probability of that is 1 out of 4. Okay, so then it says, does the mean of the sample proportions equal the proportion of girls in 2 births? So let's see. How many girls are there in 2 births total? Well, there's 1, 2, 3, 4 of them, and there's 1, 2, 3, 4, 5, 6, 7, 8 total. So 4 out of 8 is a proportion, and that equals 1/2, right? So that's 1/2. Now let's find the what does it say? Find the proportion of girls in 2 births the other way, which is, do you remember how we found expected value? We do that by taking this number, the outcome times the probability, which would be 0, plus you take this outcome times this probability. Well, 0.5 times 1/2 would be 1/4, and then you do plus this number times this probability. So 1 times 1/4, that's also a quarter. And then you add them up. So you get 0 plus 1/4 plus 1/4. 0 plus 1/4 plus 1/4 is 2/4, which 2/4 reduces to 1/2. So you get 1/2 both times when you do it. So if you calculate the proportion from these numbers, or if you calculate the expected value from these probabilities, both ways you get 1/2. So both the mean of the sample proportions and the population proportion are both equal to 1/4. No, wait, no, that's wrong. Both both the mean and of the sample proportions and the population proportions are 1/2. So they're the same, and we got 1/2 for both of them, right? So yes, both the mean of the sample proportions and the population proportion are 1/2. Yep, that's true. Does this result suggest that a sample proportion is an unbiased estimator of a population proportion? Well, when your sample proportion turns out to be the same as your population proportion, then it's an unbiased estimator. So this would be yes, it's unbiased because the sample proportion and the population proportion are the same. So it should be C. Yes, because the sample proportions and the population proportion are the same. Okay, so now let's do this one. Let's go back to StatCrunch. So an airline carries 150 passengers and has a door height of 76 inches. And the heights of men are distributed with a mean of 69 and a standard deviation of 2.8. And we want to find the probability that a male passenger can fit through the doorway. So we want to find the probability that their height is less than the doorway. The doorway is 76 inches high. So we want to find the probability that a random man will be less than or equal to 76 inches high. So click compute, and the result we get is 0.8. The answer we get is that, and then round that off to 4 decimal places. So since the next digit is a 9, we're going to round this up to an 8. Now, if half the 150 passengers are men, find the probability that the mean height of the 75 men is less than 76 inches. Now, when you find the probability of a mean, that changes the standard deviation. Okay, so how many men are there? 75 men. The mean height, it says, of the 75 men. What happens to the standard deviation when you don't have one passenger, but you have the mean height of 75 passengers? Well, what happens is you have to divide the original standard deviation by the original standard deviation by the square root of okay, so hold on, let me see, I can't see it anymore. The standard deviation previously was 2.8. So we're going to take 2.8 divided by the square root of how many men we're taking the sample of, the mean height of 75 men, so 75 men, and then we're going to get that. So the standard deviation is now that new number. So I'm going to copy that, and the standard deviation of 75 men, the mean of them, is different from the original one. So the new standard deviation is 0.3233, right? Okay, so now if half the passengers are men, find the probability that the mean height of the 75 men is less than 76 inches. Well, so the probability it's less than 76 equals 1. Okay, so 1. Round that off to 4 decimal places, it'd be 1.0000. And then it says, when considering the comfort and safety of passengers, which is more relevant? The probability from part A or the probability from part B? Why? Well, this probability is the proportion of individual passengers who can walk through the doorway. This probability right here is the probability of the average of a whole group of men to fit through the doorway. Well, we already know the average of the men is only 69 inches, so there's almost 100% probability that an average group of men, the average person in them, can fit through the doorway. So we're not interested in whether, an average basically means mean, so we're not interested whether the mean height of the men can fit under the doorway. What really only matters is what's the probability that each person can fit through the doorway, or what proportion of people can fit through the doorway without bending. So the answer to part A is the one that matters. So the answer from part A is more relevant because it shows the proportion of male passengers that will not need to bend. And when considering the comfort and safety of passengers, why are women ignored? Well, in general, now this isn't always true, but generally men are taller than women. So a design, let me finish reading through them. Yes, okay, so I'm going to go with B. So if you're wanting to include almost all men, and you have a doorway that's tall enough to include almost all of the men, then it will also include almost all of the women as well. Because of the fact that in general, not always, but on average, men are taller than women. So let me make sure that I answered everything. All right. So the next question, it actually shows you a tip. So I already typed this tip in before when I made the test for you. So click the icon to view the data set and then open it in StatCrunch. So do StatCrunch, graph, QQ plot, var1. Okay, so basically open StatCrunch and do graph QQ. Ready? So click on this, open in StatCrunch, then choose graph, and then go down to QQ, which means quintile plot. Then select var1, then click compute. Now this does not look like a straight line at all, right? So if it were a normal distribution, then it would look much more close to a straight line. So this is not a normal distribution, so I'm going to click done. So is the requirement of a normal distribution satisfied? I would say no, right? Because the histogram of the data is not bell-shaped, there's more than one outlier, and the points in the normal quintile plot do not lie reasonably close to a straight line. So I did not actually make a histogram. I did not actually, well, I did look at the outliers. There are some outliers, you can see them. Oops. Sorry about that. I accidentally made the window super big. You can see the outliers, like those outliers and things. Okay, so but the main thing is the points in the normal quintile plot. Oh, they misspelled quintile. Huh. Oh no, they didn't. Okay, sorry. Okay, so then the points in the normal quintile plot do not lie reasonably close to a straight line. Ready? Okay. No, because the histogram of the data is not bell-shaped. Do not lie. Okay, there we go. All right. And then the next problem. Okay, so I'm going to open this data set, open in StatCrunch. I'm going to do the same thing again. So graph, QQ plot, select the variable 1, click compute. Okay, so now it says select the graph below. Now this graph is a little bit taller than the other graph, so I'm going to make it wider. And then you can just tell by looking at it. So which one looks like that graph? Well, looks to me like it could be, interesting. This doesn't look quite the same. Okay. Let's see. This does not look quite the same as any of those. Let me try it again. So open in StatCrunch. So graph, QQ plot, variable 1. So I get that. So it says, hold on just a second. So it kind of looks like the middle one the most, but it also sort of looks like the last one. So I'm going to go with, I'm going to just use the middle one. Determine whether the data come from a normally distributed population. So to me, this one looks like it's almost a straight line, really close. So I would say it is normal. The points are reasonably close to a straight line and do not show a systematic pattern that is not a straight line pattern. All right. Okay, now this has a hint for you as well. Logarithms would curve the probability plot so that they would not be normally distributed anymore. So if 4 inches is subtracted from each height, would they also be normally distributed? Well, when you subtract something, it still has the same shape. And normal distribution is a kind of a shape, so the answer would be yes, they would also be normally distributed. When you multiply by something, that just stretches it out, but it would still have the same type of shape. It'd still be a bell-shaped curve. So that would still be normally distributed. And the logarithms, though, the graph of a logarithm is curved, so the logarithm of the heights are not also normally distributed. All right, well, those are your notes for your Chapter 6 test. And remember that some of your questions might be slightly different. For example, on problem 13 and 12, when you make the normal probability plots, your answers might be a little bit, might be the opposite, for example. So if your QQ plot turns out to be basically a straight line, that means it's a normal distribution. If it does not turn out to be basically a straight line, for example, if there's a curved pattern in it, then that means it's not a straight line, and so that means it's not a normal distribution. And good luck to all of you. I'll talk to you later.